absolutely. Penny is a clown right now, but your husband can get run over by a bus tomorrow. And then 5 years from now, you might find me falling. Didn't make the mistakes that I've made.
Well, I am legally Smith, but I don't tell anyone. I don't make it like everyone just calls me Herdter. That's how they know me, and that's how I feel most comfortable. So I think it'll probably just be it'll be just a transition that happens naturally over the course of years, and when we have children and whatnot.
I just meant on.
And then publishing.
I just meant manuscript.
Yeah.
I just meant publishing. Because that's where. I have my first 3 papers, as someone said, they're just gone.
Are they? Oh, well, Anywho, let's see how this goes. I guess no one's sitting in the middle seat. I don't know what happened.
All right.
Let me just...
Ready?
Or 2 days.
All right, good morning, everybody. Hello. Committee members and audience.
Cam Ainsworth is not here yet.
Oh, yes.
Oh, here. He's right here.
Oh, there we go. Yes.
Just on time.
Right on time.
How are you?
Good morning. How are you? And Shannon? Oh, there's Shannon.
Yep.
Yes.
She could see you in there.
Yes. Hey, Shannon. Good. So good morning, everybody, and welcome to Liz Herdter Smith's PhD Seminar in Defense.
Mm-hmm.
Wow. Right?
Wow.
How wonderful. And my name is Luis Barbieri, and I'm the outside chairperson for this defense committee. And Liz I'm going to let her detailed introduction be given by her major professor, but I want to point out her committee members. Steve Morowski is her major professor, and then we have Cam Ainsworth, Shannon Cascalay, Bezad Mahmoudi, and Ernst Peebles, right? So the procedure today, we'll start with the seminar, and then we're going to open up to questions from the audience, a few questions. Then we're going to have a break, a little intermission, give Liz a chance to breathe and perhaps use the facilities, take a drink of water.
Take a breath.
If nothing else. And then we return here for the actual defense part, which is an open procedure. So folks can come in, but it's going to be pretty much the Spanish Inquisition type process that we go through as a defense process is supposed to go. So with that, Steve?
Thank you, Luis, for chairing the meeting, and certainly thank you to Shannon, who's participating remotely, and the committee members. So I wanted to tell you all a little bit about Liz. Liz walked into my office in the summer of 2011.
Yeah.
And she said something like, I've been volunteering at FWRI, hauling dead manatees to the landfill. And I don't think that's a career move for me. So she said, I'd like to do, right?
I'd like maybe to try something else.
Yeah, exactly. So,
they really smell awful.
So Liz and I and Christina and a few others started longlining out in the Gulf of Mexico. So she worked as a technician for me for a while. And we had some great adventures out there, I must say. I was going to show pictures, but nah, I don't think so.
They're really bloody.
They are. Probably not right for breakfast. So Liz came on as a graduate student. For her master's degree, she looked at this question about whether or not red snapper growth had changed due to the Deepwater Horizon. So she got a really nice publication out of that in Fish and Fisheries. I think based on that, understood that aging otoliths probably wasn't the long-term thing that she wanted to do, but she got interested in population dynamics. And so she's really done a tremendous job in terms of self-education, I think, in terms of understanding this field. And now she works as a fishery stock assessment scientist at the Florida Fish and Wildlife Research Institute for Bezad. Right? So she's progressed from dead manatees to dead everything else. So today we're joined by her husband Brad, and her aunt and uncle from the other coast, Susan and Phil.
Yes.
Got it.
Yes.
Okay.
And my parents are on the live stream right now too, both of
Okay,
them.
okay.
Hey, Mom and Dad.
So even though her aunt and uncle live in Florida, like many of my students, she's a New Englander, right? So she comes from coastal Connecticut, got her undergraduate degree at BU, and I see her liberal arts skills coming into play and here, there, and certainly in terms of her dissertation. So with that, I'll give the floor to Liz.
Okay, very good. Well, thank you so much for that introduction, Steve, and so much for coming today. I'm really excited to tell you all about my research. So, well, without further ado. So, it's no surprise now that the environment can significantly influence marine resources, whether by affecting growth, mortality, respiration rates, or feeding ability. But environmental conditions are shifting due to anthropogenic climate change, and so the productivity of marine resources may be affected. And what's more, heavily exploited species may be at increased risk. Now, historically, fisheries management in the United States hasn't explicitly accounted for this environment productivity relationship, likely just due to modeling constraints, but advances in modeling capability combined with recent application and the latest federal policy that offers guiding principles to consider environment and ecosystem factors has really spurred this movement from very traditional single species assessment models to models that include additional sources of variability. Now, this ecosystem approach is really the hot ticket right now because we can use this approach to consider the links between fisheries and ecosystems to achieve a better balance between harvest and conservation. It also enables us to consider more larger scale, longer term issues like environmental condition and climate change to be considered in these models. Now, this method may be really important and useful for us in terms of fisheries management in Florida, where, as you are all aware, we have a lot of land cover and land use changes happening, as well as shifting climate zones and variation in wetland draining. In addition, we have a very, very lucrative fishery that operates at the interface with rapid human development. And one of the most targeted species in Florida is my friend spotted sea trout, or Synoecian nebulosus. Now, despite being a euryhaline species, there's a lot of research to show that distribution and abundance of this species can be affected by the environment. Factors like salinity, temperature, and nutrients really are important to this species. Now, a little bit of an aside on the importance and the amount the species has been targeted. In 2016 alone, and on the Gulf Coast, fishers landed up to 6 million pounds of this species, which by weight is equal to 3,700 Kodiak bears, or by volume, based upon rough volume estimates, could fill this conference room 44 times. So there's a lot of interest in this species. Now, despite being very, very abundant in the Gulf of Mexico, this species is an estuary fish which ranges from Massachusetts to the Bay of Campeche, and they're they spend their life in estuaries, grassy inlets, and bays most of the time. They do have a very protracted spawning period, but the new recruits quickly settle into the nursery habitats. They mature quickly. They're mostly mature around age 1, where they eventually move to sandy bottoms, and then once they reach the recreational slot, they'll soon be targeted by hook and line and nets. Now, this species is managed by the state of Florida in 4 geographical management units, and the species has been managed since the late 80s, but quantitative assessments have occurred since the mid-90s. And because this species is so high priority, there have been quite a few regulatory changes that have happened since then, as well as some additional models that have been used to assess the stock. But to this date, none of them have explicitly considered the environment productivity link happening with this species. Now, considering an environmental variable in an assessment model for a species that may have a strong relationship may help us achieve better model fit overall by reducing unexplained variance in recruitment, as well as providing a reduction in uncertainty around reference points. And then most importantly, more accurate estimates of stock status. And really including an environmental variable is really just the first step on this path to more of an ecosystem approach for this species. So this brings us to the goal of my dissertation, which was to evaluate the incorporation of environmental factors within regional assessment models for spotted sea trout in Florida. Now there are a few pieces of the puzzle that I had to put together to achieve this overall goal. The first of which was to ask about the spatial scale of population structure of this species in Florida. The second was to explore and evaluate a range of environmental factors to explore their importance to the recruitment and ask whether or not there were certain latitudinal gradients. And then finally, use these environmental variables in assessment models, testing a certain amount of configurations to see which combination offers the greatest improvement. So these pieces acted like stepping stones, sort of like climbing the mountain. The peak of this project would be to finally reach that environment component. So to jump right into the first objective, I explored spatial variation in size structure, the age-length relationship, and recruitment patterns among 6 estuary populations of this species in Florida. Now these are populations that are located in Apalachicola Bay, Cedar Key, Tampa Bay, Charlotte Harbor, Northeast Florida, and the Indian River Lagoon. And I did this by asking 2 questions and testing 2 null hypotheses. The first of which was that there was no significant differences in age, length, and growth among these areas. And the second was that there was no significant spatial covariation in recruitment among these areas. Now I did this for 2 primary reasons. The first reason was to identify the range of spatial scales over which these data could be combined for future analyses. And the second reason was to identify possible mismatches when lumping these data within our management regions, or essentially to reevaluate the unit stock assumption or the scientific basis for the management units that we have for this species in Florida. So I used 2 different data types from 2 different sources to test the first hypothesis. The first of these were fisheries independent age and length observations that were obtained from the Fisheries Independent Monitoring Group at Florida Wildlife Research Institute. Now this group performed stratified random sampling statewide and year-round, and the sampling was initiated in Tampa Bay and Charlotte Harbor in 1989. But they've since expanded their efforts statewide to major areas. They use a 21.3 meter bag stain to sample for all the new recruits or young of the year animals. And then they use a 183 meter Hall stain to sample for adults. At every sampling event, or at every time they're pulling a net or a bag, they'll record species presence or absence, and also note the habitat covariates in the area. They'll also possibly obtain a select amount of length measurements and remove otoliths for future age and growth analyses. Now the second set of data I used were fisheries-dependent length observations. So these were length observations that I obtained from the MRIP program, or the Marine Recreational Information Program. Now this is a method that NOAA Fisheries uses to count and report marine recreational catch and effort. So this is in part in-person surveys of anglers at marinas, boat ramps, or any other shore fishing sites. And the interviewers record information about effort, count, weight, or length of all of the landed fish. This is a nationwide project, but it's highly resolved on the county-wide scale. So I stratified all of these length observations to the FIM major sampling areas using the county of encounter variable. Now, I'd like to importantly tell you that I only used length data specifically for fisheries-dependent lengths starting from 2000. And then the analysis for this project, as well as all the remaining objectives in this dissertation, ended in 2015, mostly because that's when I started this project. So first, I modeled area-specific age length keys using multinomial logistic regression with the FSA package in R, so that length was a function of not only age, but also area. Then I use likelihood ratio tests to compare the age length keys among the areas. I also modeled the age-length relationship with the Von B growth equation, and then again used likelihood ratio tests to compare area-specific parameters and compare nested models. And then finally, I used chi-square tests to evaluate the distribution of age and length among all these areas. So the fisheries' dependent lengths were first truncated to a slot of 30 to 65 centimeters, which roughly matches the current recreational slot limit. And then I used chi-square to test distribution, ANOVA to compare the means between areas, and then I used post hoc pairwise comparison Tukey's test. So the results from this section indicate that size, structure, and growth are heterogeneous among areas and among areas within certain management regions. So for example, length and age, mean length and age, were significantly different between Apalachicola and Cedar Key, which are two areas within the Northwest Management Region. In addition, the growth parameters were significantly different between Tampa Bay and Charlotte Harbor, which are areas, populations that are in this Southwest region. Now, pardon me. So before I tell you about this next objective, I want to give you a primer on recruitment. So here, recruitment is the number of new fish that are settling to each area and that can then be selected by a gear. So the number of age 0 fish or new recruits is a function of spawning stock biomass generally, and it can be generalized in a few select functional forms. The Beverton-Holt form, which is depicted on the right side of the plot, is the common spawner recruit form that's used to describe recruitment of this species. Now, importantly here, young of the year abundance estimates were used as a proxy for recruitment. Now, there are some caveats to doing that. There we are. First of which is that young of the year abundance is really a convolution of recruitment. It's more like a series of additional plot twists that are happening, afterwards. So while recruitment is deterministic, we have an expected amount that we can predict based upon the functional form. Young of the year abundance, and when you're sampling for it, can include the variation due to habitat, predation, or other causes of post-settlement mortality. In addition, there may be a spatial or temporal lag between the time and place of recruitment and FIM and the sampling for these new recruits. Nevertheless, I use these data to model trends in area-specific young of the year abundance or recruitment. So I use generalized linear modeling to model the abundance and account for habitat covariates. I explored 3 model distribution types. The first of these were Poisson, and then I used the negative binomial and 0 inflated versions of the negative binomial and the Poisson. I used likelihood ratio testing and AIC to determine the best variables and which covariates explained the variation, and then to obtain variance estimates, I used least squares, means, and bootstrap. So the results of this analysis indicated that the 0 inflated negative binomial best modeled the variation in these data. And I've presented the fits to these indices here by area and by region to give you an idea of the variability in recruitment or abundance throughout the years in these areas. Next, I performed correlation analysis. So I used Pearson product moment correlation to evaluate the correlation between pairs of areas. Because there was some evidence of autocorrelation, I adjusted the degrees of freedom with the modified Kelton method, and then I used the Bonferroni correction to correct the p-values for multiple comparisons. Then finally, I modeled spatial covariance. So in this step, I estimated the spatial scale of correlation by determining the rate of decay in correlation as a function of distance between each area using an exponential covariance function. So in this equation, I was specifically interested in the V parameter here, which is the distance between areas or estuaries where correlation of the abundances would become not significant. Now, the results of this analysis can be summarized in this figure here that I will first orient you to. So on the y-axis is correlation between pairs of areas, and on the x-axis is the great circle distance between each area pair. So the black line indicates the model fit of the exponential covariance function, and the red dotted line is the v parameter, or the estimated distance between estuaries where covariation is expected to become not significant. So importantly, it occurred at 136 kilometers. So by this model, only indices from estuaries separated by less than 136 kilometers are expected to be significantly correlated. Now, after multiple corrections, there was no significant correlation or covariation among these pairwise comparisons, among these indices. So to summarize this section before I move on, first I found that there was heterogeneity in the age and size structure between select areas. I also found that there was significant asynchronous patterns in recruitment among these areas, and this could be caused by genetic differences, differential fishing pressure, or environmental factors. However, I would like to note that there was asynchronicity between indices within the same proposed genetic stock, so it may not very well be that. So considerations moving forward into the next analyses, I want to remind you that the purpose of this objective was to identify the range of spatial scales over which these data could be combined. So I deemed here that any future analyses should really be performed on the estuary scale. And then when considering possible environmental factors, it's more likely that estuary-specific factors are more influential than any large-scale climate factors, just because there was really no commonality in these indices, and that's something that you may expect to find if there's a large-scale factor that's having a very wide geographical influence. Okay, so moving on to the next objective. Here I use predictive models to determine the relative importance of a suite of environmental factors to recruitment. So I made a predictive model for each area, and I made predictive models using a method called extreme gradient boosting, or XGBoost, as it is actually called. And this is a highly flexible and accurate machine learning method, or an algorithm, that determines rank importance. And I did this for a few reasons, the first of which was to simultaneously evaluate all environmental variables at an appropriate spatial scale, to also consider variables at several time lags, and to explore a method that may be a little bit more accurate when it comes to predicting recruitment. Something a little bit more accurate than our traditional methods. So what is extreme gradient boosting anyway? Well, it is a gradient tree boosting machine learning system that was developed by Tianqi Chen and Carlos Gestrón in the computer science department at the University of Washington. And it's based upon traditional classification and regression tree algorithms. Now, this method uses a training data set with multiple predictors, so multiple x variables, to predict a response variable, or a y. And it does this by identifying dominant patterns in the predictor variable to partition the response data into homogeneous nodes using a series of decisions. So for example, here's a classification tree that classifies whether members in a specific family might like computer games. The members are classified into different leaves or nodes based upon predictor variables, and then each node is assigned a score. Now here's an example of a regression tree. In this case, there's one response variable, so one y, that is being partitioned into nodes by two predictor variables and 4 splitting points. So at the end, portions of the response variable have been grouped into nodes that are most alike one another. So this method works by recursively training the decision rule using the training data and an objective function. Here, in this application, the objective function measures how well the model fits to the training data, and it's composed of a training loss term and a regularization term. The training loss term measures how predictive the model is with respect to the training data. Some common training loss terms that you may be familiar with are mean squared error, logistic loss, it really depends upon the kind of question you're asking. And what's very neat about this method is that if you can write the loss function or the optimization function, you can use this method. So it offers a lot of flexibility if you're a little bit mathematically savvy. Then the next term is this regularization term, which controls model complexity or helps to avoid overfitting, which is important. And then the final goal here, using this objective function, is to make a simple but highly predictive model by optimizing the objective function. Really, when it comes down to it, finding the best splitting points in the data. So why this method? Well, first of all, it inherently models variable interactions. So there may be a lot of interactions in ecological systems. It's important to account for those. In addition, it can model complex nonlinear relationships, and it incorporates k-fold cross-validation in the training algorithm. Additionally, it's generally insensitive to multicollinearity and outliers, and it's wicked fast and accurate. So it has that regularization term that controls model overfitting, but it also harnesses the power of parallel computing, so the model fitting work can be distributed among multiple cores of your computer to make it one of basically the fastest machine learning algorithm that I'm aware of. So using this method, I explored environmental factors hypothesized to affect the survival and subsequent settlement of young of the year recruits, as well as factors that would affect adult spawning success. So these included salinity, water temperature, dissolved oxygen, water clarity, and water depth. And these are observations that are recorded concomitantly with every sampling haul by FIM. So these just came piggybacked with the data. I also considered river flow, precipitation, a drought index, minimum and maximum temperature anomaly, as well as dissolved inorganic nitrogen and chlorophyll A observations. Now these were observations that I then joined to the count data using a series of spatial and temporal rules that I'll soon tell you about. I also considered 3 variables that might affect adult spawning success. These included water temperature at spawning, salinity at spawning, and then general water quality. So I went to a variety of data sources to obtain these data. There's a lot of sleuthing around. I went to the USGS National Water Information System to obtain river flow data. So I obtained flow rates at the most downstream gauge location with the longest continuous data record for all of the major rivers in each area. If tidally filtered flow rates were available, those were preferred. I also went to the NOAA National Center of Environmental Information for precipitation and drought temperature anomalies. So precipitation data were obtained from the weather station that again had the longest continuous data record closest to each major estuary. And then the drought index and temperature anomalies were obtained within the National Climatological Division that encompasses each area. Finally, well, not finally, but then I went to the Tampa Bay Water Atlas to obtain information about dissolved inorganic nitrogen, at-spawn salinity, water temperature, nutrients, as well as chlorophyll A. So dissolved inorganic nitrogen and at-spawn salinity from the Tampa Bay Water Atlas were obtained, are recorded from gauges in Tampa Bay and Charlotte Harbor. Chlorophyll A observations were obtained from gauges in Tampa Bay. Unfortunately, there are no other gauges that are continuously recording chlorophyll A observations around the state. And then finally, I went to the St. Johns River Water Management District website to obtain data about dissolved inorganic nitrogen and these at-spawning success parameters for gauges within the Indian River Lagoon. Now, I told you there was a series of spatial and temporal rules, and then, so again, I'd like to remind you the top variables were collected at the time of sampling by FIM, so those were piggybacked. I didn't need to worry about those. But the remaining variables were recorded eitherly at hourly or at daily increments, so I averaged these to make a monthly average, and then these were joined by sampling month to the count data. And then select variables, including river flow, were also joined using spatial rules. So in this case, river flow was joined to the sampling event based upon the river closest to each event. So for example, in the figure on the right, there's an example sampling event that's located by this, that's indicated by this magenta star. So in this case, flow of the Little Manatee River was joined to this event because it is the closest river to all of compared to the remaining in each area. Now, dissolved inorganic nitrogen and chlorophyll A were also joined using a spatial polygon, essentially a square, based upon a 2.5-mile radius. So this was to place a spatial limit on what I could consider the closest observation of one of these to the sampling event. So on the figure on the right, again, you'll see this example sampling location. So I placed a polygon boundary, or a square, around the sampling location. And then of any sites within that square, I obtained the closest, and that was the observation I used. Now, importantly, I'd like to note many sampling hulls were not assigned a nitrogen or chlorophyll A observation just because there were no gauges within that spatial polygon to match to. Now, the adult spawning success variables were also joined temporally by spawning month, and then spatially they were averaged from observations from gauge locations near probable spawning grounds, which I have been previously identified by other researchers. So a little bit more to do before the fun part. I removed as much of the excess zeros or the zero inflation using occurrence rate thresholds. And then any sampling events where 50 or more spotted sea trout were counted were just sort of lumped into a 50+ bin. So finally, XGBoost, my favorite. All of the estuary-specific data were first shuffled, and then they were split into a training set and a testing set using the 70%, 30% rule. So the 70% of the data were used to train the prediction rule or the decision rule, and the remaining 30% of the data were withheld and used in later testing steps. So I used the XGBoost package in R, and I applied a count Poisson learning objective and a Poisson negative log likelihood loss function to train this decision rule. And then I used tenfold cross-validation to identify the number of trees that optimize this objective function. And then finally, I performed recursive variable addition to screen all the predictors to identify the best combination of predictors to produce the best model. Now here, my definition of the best model is one that had the lowest mean absolute error, so it was most accurate, and one that had the lowest mean error, so it was least biased. Now, the results of this analysis can be summarized in this one very large figure that I'll first orient you to, and then we'll take a look into. So, on the y-axis is all of the predictors evaluated for each area. On the x-axis is the gain value of each variable. Now here, in this application, the gain value represents how much the variable improved the predictive performance of the model at the time it was added. So a few takeaways. Generally speaking, relative importance of each environmental variable was consistent among areas, and then our likely players, salinity, temperature, dissolved oxygen, and depth were among the most important predictor variables of recruitment for each area, which was not terribly surprising. Importantly, river flow, very important among areas, and in Cedar Key, it happened to be the most important variable. Also, again, not surprisingly, precipitation and drought were among the top 10 most important predictor variables of recruitment for each area. They are correlated variables, so it's not terribly surprising that they would both map out that way. So to summarize this section before moving on to the final objective, I observed consistency in variable importance among areas, and any kind of specific differences I hypothesize are due to differences in estuary geomorphology, habitat, or circulation patterns. And then secondly, XGBoost really packs a predictive punch. It It was very highly predictive for all the areas. So that was a really exciting outcome of this section, exploring a new method. So then our important predictors of recruitment, not surprisingly, habitat descriptors that are describing ecological niche like salinity, temperature, and depth. And then river flow, precipitation, and drought, which are correlated descriptors that I believe or hypothesize are varying more on temporal scales like monthly and annually, which may be describing some more of the temporal variability in the data as opposed to some of the spatial variability that can be described by some of those habitat descriptors. So moving forward. Because the predictors were generally consistent between estuaries within the same management unit, I deemed that it was okay to consider single environmental factors within the current assessment models here. If, for example, predictor importance was widely different between, let's say, Tampa Bay and Charlotte Harbor, that may not have been appropriate, but that was not the case here. So using this information, moving forward, in the final objective, I evaluated environmental factors in the assessment models for spotted sea trout. And then I also evaluated the influence of forecasted precipitation on future recruitment of this species. And I did this using the 2016 assessment models that were developed by my colleagues at FWRI in the stock assessment group. And the why of this objective really brings us back to the very beginning of this presentation, where I told you that an environmental factor in an assessment model of a species that may have a very strong environment productivity relationship may just produce a better model overall, one that we can use to obtain better estimates of reference points and stock status. So a little bit about the assessment models. There were 4 regional models, 1 model for each management unit, and these were developed in the Stock Synthesis 3.24F. And this program is a statistical framework that integrates a lot of information about the stock, including catch and CPUE data, length and age compositions, and other demographic information. The models ran from 1950 to 2015, and the ages were 0 to 9 with a 10+ group. They were a 2-sex model with 1 sex-specific growth pattern. There were catch data from multiple fishing fleets, several surveys of abundance, length and age composition data, some additional demographic, and then estimates for stock productivity. So on our right is sort of the data summary for each of the model. What I want you to focus on here is the amount and number of differently colored bubbles. So models, for example, the Southwest region at the very top, this model had the greatest amount of data that were used to inform this model. Now at the bottom is really the most data poor of these. Now I'd like to add, this is not a data poor model in the grand scheme of what a data poor model could be in stock assessment, but relatively speaking here, it had the least amount of length composition data, so it's least informed. Still very informed, but least out of all here. So I used 2 inclusion methods to incorporate an environmental variable into these assessment models, and these were described by Shrippa et al. In his 2009 paper. Now, the first of these methods is one that he calls the model method. This is essentially an environmentally explicit stock recruit function. So I can remind you of the generalized form of the stock recruit function, Beverton-Holt. If you modify the error component of this term to incorporate an environmental time series, then in stock synthesis, recruitment will not only be a function of spawning stock biomass, but it'll also be a function of any variability in the environment, as well as something called a log bias adjustment, which is a pesky parameter that we don't need to go into here. The additional method that he describes is what he calls the data method. And this method, the environmental data, are essentially treated as an additional survey of abundance. And this survey is then used to tune the annual recruitment deviations, or the deviations around the stock recruit curve. So in this case, then, the likelihood component is adjusted by the environmental variable at time and the standard deviation in the error of the environmental variable. So it's a little bit different. So I considered 5 environmental factors. These were salinity, water temperature, precipitation, river flow, and drought. These were on a spatial scale which matched the management regions. So annual estimates from Apalachicola and Cedar Key were then averaged to go into the Northwest model. And then for Tampa Bay and Charlotte Harbor, they were averaged in the Southwest model. Now importantly, these annual estimates were averaged over months with peak recruitment so that the environment would be reflective of the timing of recruitment. These are variables that I used for the previous objective, so they were from the same data sources. But I have a figure here of these variables by variable and by region to give you an idea of the general variability in each. The Z score, the Z drought index is presented on the bottom because it's a Z score. It's a little bit different. I also wanted to explore something about model configuration. So essentially, would model fit be significantly improved by an environmental variable if first the young of the year abundance indices were standardized with an additional environmental variability? So in the assessment model, the young of the year index, or YOY-AMM in the magenta here, is standardized with a standardization scheme that includes not only habitat covariates, but in addition, temperature and salinity. So I explored two additional standardization schemes, one that included just habitat covariates, so this was young of the year type 1, and then an additional one that included all of the variables in the assessment model index, then in addition to precipitation and river flow. The second question I wanted to ask was, would model fit be significantly improved by an environmental variable if certain data were missing, or alternatively, if we had more data? So the specific kinds of data I'm thinking about here are length composition, age composition, and abundance indices. And these three data types generally are able to explain the variation in young of the year abundance. So for example, if these components were missing within some models, perhaps the residual variation could be explained by an environmental variable. So I performed a series of data denial experiments. So I removed each of these from model scenarios and then all combinations of the three. So essentially, this was a really large sensitivity analysis. I'll give you a quick rundown of all the different kinds of models I considered. So I used 5 environmental variables, each of which were incorporated with the model method and the data method. Then in addition to the 3 index types and then the 8 additional data complexity or the data denial scenarios, and then on top of 11 additional base runs that I built for each model type, so ones without environmental factor but with each combination, resulted in 110 stock synthesis model scenarios for each region. Now, I'd importantly like to tell you that environmental factors were considered singularly in each model. There was no model scenarios where there was more than one environmental factor. So generally, I had pretty decent model convergence, or in each case, the model was finding a minimum, most likely spot. All of the models from the Northeast region converged. The Southwest region was a little bit more pesky. It wasn't converging. Now, I then evaluated whether or not an environmental factor significantly improved a model by using the chi-square test, because 2 times the difference in negative log likelihood is chi-square distributed. So, importantly, what I want you to take away here is that of all the models tested, the largest majority of the models that were improved were from the Northeast region. And generally, these were model scenarios that included a precipitation index that had been included via the model method, and then were missing some of these length and age composition data. In the Northwest region, a portion of those were also improved, although none, no one way or the other seemed to dominate. In the Southwest and the Southwest regions, less than 1% of those models were improved by an environmental variable, so I will just say that none of those were really improved. Now, way back when, I had also told you that an environmental factor might reduce some uncertainty in the reference points. In this case, not quite. So here I've presented FMSY, MSY, and the steepness estimate from 3 models from the Northeast region, a base model, and then two 2 additional models that had an environmental index. And what I want you to see here is that while the estimate or the point estimate has shifted just a little bit compared to the base model, the variance around the estimate seems generally consistent. This is also the case for a base model with the additional Young of the Year index. Again, here, while the base estimates, while the model scenarios estimates may be a little bit different from the base estimates, the uncertainty around these estimates remain sort of unchanged. The same was the case for the Northwest region, where here the estimates were even more constrained, not much change at all. So I'd like to tell you about some important considerations before I move on to the final part of this objective. I really hypothesize and think here that performance of an environmental variable is really related to the amount of data. So if you remember, I told you that the Northeast model was generally the most data poor, has the least amount of length and age composition data. Importantly, though, the length of an environmental time series can affect its performance, as well as something called the first year effect, or how close the first year of the environmental time series is with respect to the end year of the model. I'd also like to tell you that there are very, very strict assumptions of the model method, which means that we need to be extra judicious when we interpret these results. However, environmental data for possibly other data poor models might be a high win, low loss method. These data are freely, like precipitation data are freely available, and so it may be worth it for other less data heavy models to test an environmental variable. And if it doesn't work, that's okay. So in terms of reference points, again, I showed you that the reference points were highly insensitive and really seemed to be constrained. And I hypothesized that they're really constrained due to natural mortality and steepness. These are 2 parameters in assessment models that are really strongly affect the estimate of reference points. So if they're fixed through all of the models, it's not terribly surprising that the reference points, may not be changing. So in these models, natural mortality was fixed and steepness was really only varying within a narrow prior distribution. I'd like to explore some additional model scenarios that have some extra sensitivity where we can explore letting M and steepness range. So the final section here was then to evaluate the influence of forecasted precipitation on recruitment estimates. Now, I chose precipitation, first of all, because it improved the assessment models for the Northeast and the Northwest region, and it's a forecastable parameter that can tell us a little bit something about future climate. So I obtained statistically downscaled precipitation estimates from Dr. Vasu Misra and Dr. Amit Bhardwaj from the Florida State University Center of Ocean and Atmospheric Prediction Studies group. And they produced these estimates for mid-21st century Florida, so 2041 to 2060 for both the Northeast and the Northwest regions. They produced these estimates at a representative concentration pathway of 8.5, which is about 700 parts, twice of where we are right now. And they produced these estimates using 2 circulation models, which really essentially differ in terms of the way they're modeling moisture flux off the continental shelf. So here a figure that depicts the precipitation estimates. What you can see right away is that the Northeast region in red precipitation mid-21st century will be highly variable, which is not terribly surprising considering expectations of climate change. So I incorporated these precipitation forecasts in the assessment models using the model method that I just told you about. And then I used the forecast feature of stock synthesis to produce precipitation adjusted annual estimates of recruitment for 2041 to 2060. And I did this at 3 fishing mortality levels, FSPR 25, 35, and 45%. So the results of these forecasts can be summarized in these figures, which I'll walk you through. So I have presented historical recruitment for each region plotted next to forecasted recruitment with precipitation index. I also presented the error range. So importantly, I want you to take away that mid-21st century recruitment will be variable. However, the error range around these estimates preclude the use of these forecasts for absolute estimate values, but it's really just more of a strategic plan. What might be our situation come this time? So important considerations here. There are very strict assumptions of the model method, which I just told you about. And in general, there are very strict assumptions of forecasting in these assessment models. They assume constant selectivity through the duration of the forecast, as well as constant fishing pressure, which might not be a great assumption to make, but that's just what they are. Additionally, only one possible emission scenario is evaluated here. There are, I believe, at least 6 that are acknowledged and recognized by the EPA. Also, there's very strict assumptions of circulation models. Generally, they can really only approximate certain processes. So, there's some error. Finally, this is only one environmental factor, just precipitation. There are many others that may be affecting this species, but it's really good to just take a snapshot and think about what might happen, just to get us on that step forward, thinking about making a plan. So you've made it, but if you're just tuning in, I'd like to give you a snapshot of my dissertation. First of all, I explored variability in population dynamics and recruitment of 6 estuary populations of this species in Florida. In addition, I evaluated estuary-specific environmental predictors of recruitment using a novel machine learning method. And then I used the environmental predictors in regional assessment models of this species. In the first section, I found that mean, age, length, and growth were heterogeneous among areas, and that there was no significant covariation in recruitment. And I hypothesized that the differences are likely due to the direct influence of estuary-specific environmental factors. In the second section, I found that our likely players, salinity, water temperature, dissolved oxygen, river flow, and precipitation were all important predictors of recruitment, and that any specific differences are probably due to geomorphology and circulation patterns. So that's really important when we come to think about specifically for one area, which variable is important given the habitat and the geomorphology in that specific area. Then finally, XGBoost has a really high predictive power, and I think this project was really neat, but I think this section was my favorite because it's such a novel tool, and I think that it might be a really useful method that we could explore in other applications in fisheries science. Finally, for the last section, generally it was a precipitation index that improved the Northeast model, but I hypothesized that model complexity really influences the performance of an environmental factor. So if the models are missing length and age composition data, there's a lot of residual unexplained variation, and that index, that environmental index, can step up to the plate and say, like, hey, I can describe some of that variability. Finally, the reference points were marginally affected, but I hypothesized that this is due just because of the fact that natural mortality and steepness were really constrained here. So possibly it might be a different result if we could explore some other things. So that was a lot, but there's always more to do, as we know. So I'd like to think about some sensitivity testing when natural mortality and steepness are allowed to range, as well as perform some simulation testing to evaluate whether an environmental variable not only improves our model, but will it actually really help us achieve our management targets. So there's a little bit of difference there. I'd also like to explore the utility of some additional spawner recruit functions in the newest model of stock synthesis, and then work on continuing evaluating this environment recruitment relationship. These relationships are known to break down over time. There have been a lot of researchers that have declared a significant relationship, and then with the additional few years of data, all of a sudden, nope, not significant. So this is a project that really you can never close the book on. But I think that it's really important to consider this work in the broader context of habitat and fisheries management in Florida. So I don't need to tell you all that there's a lot of evidence that land use and climate change will impact Florida stocks. So I suggest that we're really promoting management strategies that promote the resistance, resilience, or adaptation to change. So for example, removing threats or additional stresses like invasive species and managing habitat loss, and making sure our fishing pressure is not through the roof, as well as expanding protected habitats by identifying disproportionately high areas like nursery habitats, or areas that are just like producing just an overwhelming amount of new recruits, like essential juvenile habitat. In addition, working on ecosystem restoration efforts that, such as those that are addressing like ecosystem degradation due to human effluent, and then managing our watersheds. So we have some success stories in Tampa Bay in terms of managing our habitat that have helped our stocks, specifically spotted sea trout. So the Tampa Bay science community within the last decade has worked really hard to improve the seagrass beds in Tampa Bay and the overall health. But as you all know, we have some current issues that we need to address. And then finally, management strategies and actions. For this stock specifically, it's really important that we're constantly ensuring that we have a very developed age structure to buffer against years with highly anomalous recruitment due to really bad environmental conditions. And this is something called the storage effect. We need to make sure that there's very strong store or set aside, like we're squirrels, like keeping some safe just in case, something awful happens. So we can do this by, obviously maintaining our slot and bag limits, or doing some slot and bag limit analysis. There have been some students at UF that have done some slot limit analysis of this species. And just really maintaining our SPR thresholds. So to achieve sustainable limits for all areas, we're doing really well in the Southwest and Southeast region. We're not doing very well in the Northwest and the Northeast region right now. So clearly we have a little bit more work to do. Now, I have a lot of people to thank for keeping me on track here and off this perilous, winding PhD path. I did not make this figure. I found this on the web, so clearly this is not just my experience. This is a shared experience here. I'd like to thank Steve. I came to Steve, I knew nothing, and he brought me out on the boats and said, all right, we're going fishing, and just, believed in me all the way, and that's really awesome. And then, my committee members, Cam and Shannon, Behzad and Ernst, for really thinking critically about parts of this and really offering advice, as well as my colleagues in the stock assessment group, Bob and Joe and Dustin and Joseph and Shanae and Chris and Mike. Wholeheartedly, this project would not be what it is now without you all. The number of times I just would ask any one of them, hey, what do you think about this? Hey, what do you think about this? What do you think about this? They're just all so great and willing to engage me in any conversation about this project. Obviously, my fellow minions and all my friends, you're all great. You can't, you can do it, but it's really awful if you don't have a great support network of friends, as well as CMS faculty and administrators who are, so pivotal. Make sure that our tuition is getting paid, that, we have health insurance, we have all these important things that we need as graduate students to really keep the bus running. I'd like to also acknowledge my funding sources, the MRA Fellowship, the George Lorton Endowed Fellowship, the Guy Harvey Foundation Scholarship, and very generous support from the CIMAGE Consortium along the way. And obviously my family, hi Mom and Dad, on live stream, and my husband, Brad, who seriously, he's awesome. He deserves some major co-author status because he helped me so much with, writing some of the scripts to build those spatial polygons with fuzzy lats and logs with. He happened to have some expertise in, so that was great. And then finally, my dog, because you all know that when you walk your dog and you're stuck on something, just having the mental clarity to say oh, wait a minute, this is what I'm gonna do next. I can't tell you the number of times I've walked my dog and just had some clarity. I'll be happy to take any questions now.
Liz, excellent job. And we're going to open the floor then for general questions from the audience.
Louise, I think, yeah.
Just a question about the covariability of river flow, precipitation, and its effect on salinity.
Mm.
I noticed that you had separated salinity is in the spatial frame, but river flow and precipitation in the temporal frame.
Mm.
But I would think those temporal changes would also affect the salinity in the temporal time frame. How do you deal with that?
Yeah, that's a good question. In terms of it in the modeling, like in the XGBoost model, what's neat about that is you don't have to explicitly declare any kind of functional relationship between temporal variability in river flow and then how it's affecting the yearly spatial variation in salinity. What's the paradigm between like a traditional model where you're saying this is the model, this is the relationship, let me find the best model is different. That prediction method assumes that these response data are a result of salinity river flow, and it's a random, very complex process that it will just eventually learn. So what's neat about it is that like it's learning for you as long as you're providing it appropriate ecological context and really setting up, really helping it to solve that.
Can you have over here first?
Pretend like I'm not a scientist,
Okay.
and I'd like for you to give me the 3 or 4 bullet rundown as why I should care about any of that.
Yeah. Okay. Well, spotted.
By the way, I am a scientist.
Yes, I know. Hi. Thanks for coming today. Yeah. Okay. So spotted sea trout's a really important stock in Florida. It can be affected by environmental variables. We have a lot of land use river flow changes in Florida. As you know, many of our rivers are impounded. So accounting for the variability in the assessment models is important for us to capture some additional source of variability. It helps us to produce better estimates of stock status, which is really what we need to be effectively managing this species. So it's taking the ecology and the variability in the environment, putting it all together and saying like, okay, what does it mean for management?
You, sir?
Yes, as a writer, I can appreciate the continuity and clarity of your presentation, so props for that. You were excited by the machine learning predictability in XGBoost.
Mm-hmm.
So, and because you're the kind of person that has wheels turning all the time, whether you're walking a dog or not, I wonder what you can predict for the application or use of the machine learning research.
Yeah, that's a great question, actually. So let me just give you a background on XGBoost. It's really, really new method, but it's based on some like general gradient boosting methods. So I actually stumbled upon this XGBoost application when I was talking to John Freschke, who's a scientist at the Gulf Council, and he had used gradient boosting to explore environmental variables for spotted sea trout in Texas, southern flounder. And that gradient boosting is based upon some research by people in New Zealand who use this method to predict species richness, species distribution. Now for XGBoost, there have been some recent applications, and actually researchers in China have used it to predict vessel type based upon VMS fishing speeds. Which I think is really novel and something that some researchers in this university have really spent a lot of time thinking about. I've seen some other people use it to predict spawning site location. So you can also extend it and sort of use it almost in like a habitat suitability modeling kind of type. So I think there's a lot of application. Those are just some that are at the top of my head.
Does that kind of answer this lady's question about why should anybody care?
Well, yeah, that is specifically about that model, that one objective, but the whole project, putting it together.
Sue.
Hi, Sue.
There's no one to sit behind.
I can see all sorts of applications for that in the future, so really